classical image processing works until production reality changes. In this video we'll see why this happens and why machine learning has become essential for reliable surface inspection. This is the first part of a free video learning series on automatic visual surface inspection. It explains why optical surface inspection is, where it is applied, why classical image processing approaches reach their limits, and why machine learning plays a central role in reliable detecting surface defects. Together, the three videos build a solid foundation for understanding, evaluating and comparing machine learning-based visual inspection systems in industrial practice. Optical surface inspection means visually examining products to decide whether they are good or defective. This inspection does not primarily focus on the function of the product, but on its visible characteristics, such as scratches or other optical deviation. To reliably detect such defects, every surface and every edge of the component must be inspected. These defects often originate from the production process itself, for example due to incorrect handling, tool wear or slowly changing process parameters over time. Optical surface inspection is used in many industries to reliably detect visible defects. Typical applications include electronic manufacturing, the automotive industry, textile industry, and the food industry. In the past and in some cases still today, many inspection tasks are performed by humans. But manual inspection quickly reaches its limits. Attention drops after a short time, which can lead to errors being overlooked. Furthermore, evaluations are subjective and not always reproducible. Two inspections might evaluate the same defect differently. In addition, manual inspection is not suitable for high volumes. Automatic optical surface inspection was developed to enable the effective testing of high product volumes. At its core, it works like this. A camera captures images of the product and algorithms analyzes these images based on defined rules. Each image consists of many individual pixels with different brightness and color values. These are evaluated using classical image processing to detect defects and evaluate the product. Based on this, let's look how classic image processing works. Images are systematically processed to make relevant features visible, which then determine the product quality, so whether a product is evaluated as good or defective. Filters are used to enhance certain features, increase contrast, or reduce image noise. Subsequently, fixed thresholds define which images are considered relevant. An image goes through a fixed sequence of processing steps. In the end, a binary result often emerges, defective or not defective. For clearly defined errors, this approach has proven very effective, but reaches its limits when surface appearance varies or when illumination and material property change. The central problem with classic image processing is its strong dependence on many manually defined parameters. Thresholds, filters, and decision-making rules must be specified in advance. Even small changes such as variation in illumination, reflections, or natural materials fluctuation can significantly reduce detection reliability. Any process change therefore requires parameter readjustments. As a result, classic image processing is difficult to maintain, poorly scalable, and associated with high engineering effort. To overcome these limits, machine learning is increasingly being used. Many machine learning models independently learn from data which image features are relevant for evaluating component quality. This feature extraction is no longer done manually, but directly from many training images. This makes the models more robust against natural variations in the production process and less sensitive to external influences. Data is a central success factor. The quality of the result depends directly on the quality and diversity of the training data. Only when the data realistically represents the actual production environment does a machine learning model make a reliable decision. If certain defect types, materials, or process states are missing from the training data, the model will not be able to recognize them later. A model learns exclusively from what it has seen during training. Another common problem is the inconsistent labeling, which introduces contradiction into the training set. As a result, the model cannot learn clear correlations, significantly degrading performance and leading to uncertain or incorrect predictions. In summary, optical surface inspection is indispensable in many industries. Classical image processing can solve simple, stable tasks reliably, but reaches its limits with variable processes. Machine learning provides a decisive advantage by learning relevant features directly from data, making it better to adapt to real production conditions. However, the success of such system depends heavily on the quality of the image data. Only the combination of suitable image acquisition, consistent data, enables reliable automatic inspection. In the next video, we will take a closer look at image acquisitions, hardware and data, and show why these factors are often even more critical than the machine learning models itself. Finally, in the third video, we'll explore how data is transformed into a functional machine learning inspection system, which approaches are used, and where the limits of these models lie in production. Thank you for watching. For further information, individual courses or implementation of inspection systems, please contact us. See you in the next video.
You're the signal in my static hum.